mispronounced your last name,
No,
from
that's very
Bonn,
good.
who will tell us about fusion rules for supergroups. So please, Thorsten, take it away.
Okay, so thanks a lot for the opportunity to speak. So basic question is, if you have a, let's say C is some representation category. So of course, I don't want to really define what I mean by it, but for instance, representations of an algebraic group, or and this could be in characteristic 0, or it could be in positive characteristic, or it could be rep UQG. G is a complex semi-simple Lie algebra, and let's say Q is the root of unity to make it more interesting. Or it could be later on the representation category of supergroup. Then I can take two simple modules, L1, L2, and I can take the tensor product, and then I can decompose it into indecomposable summands. And of course, I would like to understand now this decomposition into indecomposable summands, and this is in general very, very hard, even if you are in a semi-simple world. Think about the case when you take representations of the symmetric group. There's still something we don't understand. Now, when you move to Lie theory or algebraic groups, then sometimes we have complete answers. So for instance, if you take semi-simple complex Lie algebra and you take finite dimensional representations of it, then there are several approaches to determine this decomposition. And in that case, the indecomposable objects are all actually irreducible by Weil's theorem. But if you, for instance, move to representations of an algebraic group in positive characteristic, or you are in this root of unity case, then typically very, very little is known. And so today I want to look at this case when C is equal to rep G. And so these are the finite dimensional representations of an algebraic supergroup in characteristic 0, or simply over the complex numbers. And I will focus on two cases. Before I specialize, let me say that in this generality, and even for these special cases, this question is completely open. So virtually, I mean, very, very little is known. In general, we have no formulas for the decomposition or the multiplicities of indecomposable objects. We have no, even once in a while when we know that things decompose in a certain way, we don't know how the indecomposable modules look like. So all in all, very little is known. So the main example, or let's say the example for the first half of the talk, is GLMN. So for the sake of such a talk, it's easier to talk about Lie superalgebras than talk about algebraic supergroups. So the Lie superalgebra GLMN is obtained as follows. You take a Z2 graded vector space, and unfortunately many years ago people called this a super vector space, and then you look at all endomorphisms of this Z2 graded vector space. So those which preserve the pairing, the parity, though they move V0 to V0 and V1 to V1, and those which switch the parity. And so if you look at these endomorphisms, this is typically called GLV. And once you choose a basis of V0, once you choose a basis of V1, so everything here is finite dimensional, then you can identify V, and let me work over the complex numbers here, with a Z2 grade vector space as follows. So there's a C to the M in degree 0 and C to the N in degree 1. And then I will typically call this here GLMN. So every Lie superalgebra has an even part and an odd part, and you see this very nicely here for GLMN. So if you take an arbitrary element, then you can think of it as a matrix, as a block matrix A, B, C, D. So A here is an M cross N matrix, D is an N cross N matrix, and B and C are mixed, M cross N or N cross M. And of course, then you have special matrices, which have the following form, A, 0, 0, D. And these matrices, they are the even part. And you see this is just GLM cross GLM. And when I talk about representations of such a Lie superalgebra, basically, I mean, it's the same definition as for a Lie algebra, essentially. Just that I don't look at vector spaces over C, I look at Z2 graded vector spaces over C. If I have such a C2 graded vector space, I have this GLV here. I should say that now I need to introduce a structure of some Lie algebra or Lie superalgebra, and I use the so-called super commutator for this. So this is just basically like the usual commutator. So X commutator Y is XY minus, but then I throw an additional minus sign inside, and the minus sign depends on the parity of these elements X and Y. And that makes it into so-called Lie superalgebra, GLMN and GLV. And the representation is just then basically a morphism from GLMN to GLV for some Z2 graded vector space V. And this defines my category of representations, rep GLMN, and everything seems to be extremely similar to the GLN case, just that things are not similar because this category fails to be semi-simple. And so, well, the general techniques from let's say standard Lie algebra course are pretty useless, and so the theory has much more in flavor with, say, category O or modular representation category. So I said above that I want to sort of study algebraic supergroups or representations of this. So I will not consider all representations of GLMN or of Lie superalgebra. I will only consider those that are algebraic, so they live to the algebraic group. And so an ad hoc way to define this is the following. I just take all finite dimensional representations of GLMN such that this subalgebra G0 acts semi-simple. Okay. And this is then the same as finite dimensional algebraic representations of the algebraic supergroup GLMN. Okay, so I already said it, but this category, in case you've never seen this, is not semi-simple. And so if you take a tensor product of two, you will in general only be able to decompose it into indecomposable objects. And then the question is to describe these indecomposable objects. So I think one nice way to think about the category and the failure of semi-simplicity is to introduce the notion of atypicality. So this category decomposes into blocks. And we can assign a number to each block which measures the sort of failure of semi-simplicity or how complicated the block is. And this number is called the degree of atypicality. So this is a number between 0, let me denote this like this, and n, where I assume here, without loss of generality, that m is greater or equal to n. So one way to think about this category rep GLMN is the following. So below, sort of, you have your atypicality 0 blocks. In fact, for atypicality 0, they're all semi-simple. This is a semi-simple part of your category. Then above, you have somehow your atypicality 1 blocks. This is somehow the tame part, because all these blocks have tame representation type. And then from atypicality 2 onwards, you have wild representation type. And this goes up then till atypicality n. And this is somehow, these are somehow then the most complicated blocks. And you can measure this precisely. For instance, you can talk about the complexity of modules, and this increases with the atypicality. Or you can look at the Löwy length of a projective cover, and basically the Löwy length of a projective. So the Löwy length of a projective cover of a simple of atypicality k is 2k plus 1, and so forth. And this gives also a fruitful way to think about these tensor product decompositions. So we know how L lambda tensor L mu looks like if, so the atypicality of lambda and the atypicality of mu are less or equal to 1. So, and then in this case, we can write down the decomposition into indecomposable summands, and we can also describe these indecomposable summands precisely. For instance, I could write down the Sokal filtration for each indecomposable summand. But beyond that, almost nothing is known. And there's one more thing that is known, and that's something I started a couple of years ago. This was a joint project with Weissauer. We have so-called truncated tensor product decompositions. So what do I mean? I want to truncate at the representations which have superdimension 0. So you see, a representation is a super vector space. Super vector space has an ordinary dimension, just by adding the even and the odd part. But you can also subtract the odd part, the dimension of the odd part, from the dimension of the even part, and that's called the superdimension. So that's actually the natural categorical dimension in the super world. And then it can happen that the representation is superdimension 0. In fact, that's a generic case. You can prove that it's a result of Saganova, that in fact, if you take GLMN and you take an irreducible representation of GLMN, then its superdimension is non-zero if and only if it is maximal atypical. So all these lower blocks, they don't give you anything, but some other approach in this truncated decomposition is to understand the category from the top, from the most complicated part. So what do I mean? So I take L lambda tensor L mu, and I decompose it into something. Let's call these indecomposable things II plus superdimension 0. Yeah, and in this case, so I did the case GLNN 2-3 years back. And I want to explain two things today, basically. I want to explain the case M different from M, how you can reduce to the M equal to N case. And I want to say that this basically, this approach works also for OSP M to N, so-called autosymplectically superalgebra. And if time permits, I will make some conjecture about these indecomposable summands of non-zero superdimensions that occur here. So it seems a bit weird that you can say anything about such truncated decompositions because we just learned that the maximal atypical part is the most complicated one. And there's a reason why this works, and this is based on a deep theorem of Deligne. Namely, when you take your category and you throw away all indecomposable objects of superdimension 0, you have to make this you have to make it the right way. You have to quotient by the so-called tensor ideal of negligible morphisms. You get the representation category of a supergroup scheme. So you have a lot of structure in this quotient. That's basically the main reasons why you can say anything about these truncated decompositions. So formally, to make this truncated decomposition rigorously, take rep GLMN and you mod out the so-called negligible morphisms. And whenever you quotient a tensor category by some tensor ideal, you still keep a symmetric monoidal category. If the previous category is rigid, the quotient is rigid, and so on. Now, the nice thing about quotienting by the negligible morphisms is that this is semi-simple and abelian. Okay, you could call it, it's a so-called pre-Tannakian category. And now there's a theorem of Deligne which characterizes basically so-called super-Tannakian categories. So it's an extension of the notion of a Tannakian category where you allow, which encompasses not just algebraic groups or affine group schemes, but also supergroups, affine supergroup schemes. So this is an incomplete sentence here. So by a theorem of Deligne, this quotient is equivalent as a monoidal category or tensor category to finite dimensional representations, rep, and I call this red here, like reductive, of a supergroup scheme G-red. And ignore the epsilon. I just wrote it down because I don't like to write down wrong things. So this epsilon has the effect of sort of, it's a full subcategory of the full representation category, which I think is not so relevant for the talk. In general, if you take, let's say, rep GLMN and you quotient any other tensor ideals, you don't get anything reasonable anymore. So the major thing is you still have a representation category. And you see this is a semi-simple representation category. And that's a very, very harsh condition in the super world because you almost never have semi-simplicity. In fact, for instance, if you, there's a structure theorem which tells you basically any such algebraic supergroup of semi-simple representation category is some product of reductive groups and then groups of type OSP 1 to R. So this is one family of supergroups which is easy to understand. So essentially, this quotient is almost like a reductive group, but it might not be a finite type. So it might just be a pro-reductive group. And so it's a natural question to understand this, this G-red. And it turns out that if you analyze this G-red in the case of GLMN, you basically get a product of classical groups. So you might have seen such a construction before. For instance, if you work with a quantum group at the root of unity, you have the subcategory of tilting modules. and then you semi-simplify the subcategory, and you get a fusion category, and that has been studied a lot in context of three-manifold invariance and so forth. But in a certain way, this quantum case is way easier than the supergroup case, because first of all, you only have finitely many objects where the quantum dimension doesn't vanish. In fact, these objects in the fundamental alcove, they're anyways all irreducible, and you have some control over the tensor products, because, well, you can control sort of the Weil modules in the filtration with Weil modules of the tilting module. Okay, so it seems that you cannot say a lot in the super case, but that's wrong. But one should not consider the whole category rep GLMN. One should go to a simpler subcategory. One should go to basically the subcategory generated by the irreducible representations. So I denote by TMN plus the following subcategory. The full subcategory of indecomposable summands in iterated tensor products of irreducible representations of superdimension greater or equal to 0. Okay, so I take irreducible representations. I don't want irreducible representations of negative superdimension, and I can, without loss of generality, actually do this, because if I have any module, I can take its parity shift, and that will turn negative superdimension to positive superdimension. So this is a harmless restriction. And then I pick up all the indecomposable summands, and I tensor everything together, and that's my subcategory. And I semi-simplify this. Okay, and this is again equivalent as a tensor category to some, now I need a new name, maybe red, irreducible. And I almost can determine this group. And turns out this is just a product of SLs or orthogonal groups, symplectic groups. And the way to prove this is the following construction. So it seems that determining this group is totally hopeless, because we hardly know anything about tensor product decomposition. So we don't know what indecomposable summands occur. So how do you actually say anything meaningful about the quotient? I should say, in order to not to be too optimistic, sometimes we cannot determine the full group, but we can determine what is called its connected derived subgroup. And the reason is that a priori these groups here, these G red ir, in the GLMN case or in the OSP case or in any other case, there's no reason why they should be connected. So anything could come up as a connected component, and seems to be extremely difficult to rule this out. So we don't understand some of these character groups in general. So the crucial tool is a construction which is due to Duflo and Saganova. And this is a very general construction. You take a Lie superalgebra, finite dimensional, for instance, GLMN, and you pick an odd X. Odd means it's in G1, such that its supercommutator vanishes. And then if V rho is a representation, you can look at the action of this X on V. And if you do it twice, then this the vanishing of the commutator means that the composition is 0. And so you can talk about cohomology, and then we said ds of V is a kernel of rho x divided by the image. And it turns out that you can interpret this ds always as a module under the algebra. It's again a least superalgebra, but of lower rank. So the aim is somehow to reduce things to lower rank. Gx, well, kernel of at x divided by image of at x. And then you obtain a functor depending on x. And this turns out to be symmetric monoidal functor. So this is a functor that you can use to reduce many, many questions to lower rank. This Gx might look a bit mysterious, but if G is GLMN, then Gx is simply GLM minus R, N minus R, and this number R is something that depends on X. Could be anything, could be 1, 2, whatever. So it's in a certain way, you might think of this as a replacement for the restriction functor. Of course, we have a restriction functor in the superworld, just that we don't know anything about it. And this dsx can be sort of understood. Let me know when I should make a break, otherwise I'll continue with one theorem.
So this is a good spot to take a break if you're ready, or?
Sure, it's fine with me.
All right, excellent. In that case, let's take a 5-minute break. And if anyone has any questions for Thorsten, this is a good moment to ask.
I have a question. Are there like particular chains of these stabilizers GX that like work your way all the way down, m minus 1, n minus 1, n minus 2, m minus 2, all the way down to?
Right. So, for instance, you can take, so here's, for instance, an x that you could take. You have zeros everywhere. Just you have a little 1 here. And this is one x that you could take. And well, you go from, let's say, GLMN to GLM minus 1, n minus 1. And then you can basically pick the same x again and you iterate this. And so if you iterate this long enough, sort of ds, ultimately you get a functor from rep GLMN to rep GLM minus n 0. Yeah. So this here on the right-hand side, these are super representations of GLM minus n. Yeah, so that's what you can do. You can iterate this, but you could have also picked the following x. And then you would have not gone down by 1, then you would have gone down as many r's as they are here on the antidiagonal.
So is there some sort of analog of a degenerate affine Hecke algebra acting on these iterated things? I assume that doing that final x is the same as composing all these previous x's?
That's very, very complicated. In general, the answer is no. It is the same if you just compute ds of an irreducible. So when you take an irreducible module and take ds to the 1 steps down, it's the same as when you take a big x. But for an arbitrary indecomposable module, this might not be true. I don't know if there are counterexamples for GLMN, but there are definitely counterexamples for other simply superalgebras. And analyzing this difference between iterated application of ds and some of the big ds is tricky. They're related by some spectral sequence. And if you take irreducible L, you can show that this spectral sequence degenerates at the E2 level, and then you get this result. But in general, I think this is an open question, how they are related.
Are there natural transformations of functors that?
No.
And I guess finally, does ds have an adjoint?
Actually, I don't know.
Super interesting. Thanks.
So we actually have a comment from Ina Isenbud, who's telling us that it shouldn't, that since it's not exact on either side, it should not have an adjoint. So maybe she meant to send that to everyone, but.
Yes, sorry, my mistake.
No, it's okay. All right, so we're actually at the 5-minute mark, so why don't we continue with the talk? So Thorsten, please take it away.
Okay, so you have these DS functors now, and you want to somehow use them to understand the semi-simplification. Some of the crucial theorem, I guess, is so I introduced above, let me just go back quickly, this category TMN plus, full subcategory of indecomposable summands and iterated tensor products of irreducible representations of superdimension L lambda greater or equal to 0. And I want to understand its semi-simplification. And then DS sort of induces then a functor between the quotients, between the semi-simplifications. And I'm working here with the case, let's say, where I go down in one step, but the theorem would be true for also for bigger steps. So we have this induced DS functor, and so you want to understand now, so basically the strategy is now to say, okay, maybe if I go down far enough, then I understand the semi-simplification, and then I use this to inductively go back to the case, to the general TMN case. And I should say the theorem here is use a lot of machinery. So for instance, as a special case, it includes that when you apply DS to an irreducible representation, then it's semi-simple. It also contains as an input that when you take DS of L lambda, and L lambda had a positive superdimension, then all the irreducible summands have positive superdimension. Otherwise, you would never get this induced functor here. And so this is somehow something I will not talk about. I'll just use as a black box. And so let me maybe give these representation categories that you see here a name. So I call this here maybe HM minus 1, N minus 1. So this is this supergroup scheme such that rep of this supergroup scheme is equivalent as a tensor category to this quotient. And here's HMN. And then maybe part 2 of the theorem is that this HM minus 1, N minus 1 is a subgroup of this HMN. And furthermore, that that HMN is reductive. So there's no super here anymore. We've thrown it away somehow. And so, and part 4, and I'll just write it in a short notation. So DS is the restriction functor. So in 2, I consider this embedding, and then I can, of course, restrict representations of HMN to this subgroup, and DS gives me these branching laws, the branching rules. Okay. And so using the theorem, we were basically able to determine these HMNs in the case M equal to N. So what do you do if you're in the case M different from N? So here's a slogan, how to think about this. So if you take an arbitrary irreducible representation, but maximal atypical, so that its superdimension is non-zero, then I can understand it combinatorially by assigning to it a so-called weight diagram. And then I can assign to this weight diagram a cap or arc diagram.
Thorsten, somehow we can't hear you.
Yeah, Thorsten, something's off.
We couldn't hear you since the start of the slogan, sorry.
We still can't hear you somehow. Something.
Can you hear me now?
Yes.
Oh, I'm really sorry. So I mean, I somehow touched the microphone button. So this is the highest weight of an irreducible representation, and I can assign to this a weight diagram. And basically, I just take these lambda i's, and in a certain way, I label the number line, z, by certain symbols. And maybe the exact rules are not so important, but at the end, so this here is z. At the end, I have certain symbols on my number line. So I have crosses, maybe like this. How many do I have? M minus n crosses. And I have downs, maybe like this. How many do I have? So I said I have a maximal atypical weight. Actually, the number of these downs, that's the atypicality. So I have n of those. And all the other things, if you want, you can leave them free, or you can label them by ups. And this weight diagram determines my weight uniquely. And thinking in terms of these weight diagrams and so forth is a very useful way in understanding the combinatorics of the category. You can describe X1s or duality and superdimensions, everything in terms of these weight diagrams. But I want you to think of this weight diagram as consisting of two parts. So here's one part where you just keep the crosses. So I mean, I have to decrease it somehow. You ignore all other symbols. And in the other part, you just keep these atypical things, these downs. And I mean, all the other symbols, the ups, they're just junk. They're just there. And so what you see here are these are the so-called core symbols. In that case, there are 3 here. So I would be in the case of GLM plus 3 M. And so I said above that when you take ds and you go down all the way, you eventually end up in rep GLM minus N0. And in fact, what happens here when you take an L lambda, it goes to a representation that is denoted by like this, L core. In fact, that's not completely correct. It comes with a certain multiplicity. So it's an isotypic representation of GLM minus N. And this L core doesn't really depend on lambda. It depends only on the block of lambda. And that's what you see here, basically. This here is L core. Yeah, so this is basically when you would take ds to this weight diagram, and you go down all the way till GLM minus n, that's what you get with a certain multiplicity. So that's one ingredient. And then this here, you see there are no crosses anymore. So there are no crosses anymore, exactly as if m was equal to n. So this here actually determines uniquely a weight in the principal block of rep GLNN. And in fact, I mean, there is so Saganova constructed certain explicit block equivalences. She proved that if you take a block of atypicality K, then it's equivalent to the principal block of GLKK. And so here in the maximal atypical case, you end up in the principal block of rep GLNN. So I have to be a bit careful. This weight, what you see on the lower right-hand side, is not exactly the image, because sort of in order to apply this block equivalence, I have to remove the crosses. And then there might be shifts I have to fill up. But up to these shifts, this is the basically equivalent weight in the principal block of GLNN. And so the slogan is up to superdimension 0. L lambda is so this is this isotypic representation of GLM minus n that I get when I apply this ds functor repeatedly. External tensor product. With this here, I have to give it a name. So in what sense is this true? So, I mean, for instance, there's a superficial way in which it is true. And you see this basically here in this part. If you look at this here, this ds functor is a symmetric monoidal functor. It preserves superdimension. So the superdimension of this isotypic representation must be the same as the superdimension of L lambda. And so this m lambda, in fact, depends not at all on the crosses, this multiplicity. It only depends on the so-called arc diagram of this here, which is independent of the block of the crosses. So the superdimension m lambda times L core, you already have this mixing. This m lambda only depends sort of on the equivalent weight for GLNN, and this L core only depends on the block type. But it's better than this, namely HMN. Oops. So HMN. This was this group that was controlling my semi-simplification. Is GLM minus n direct product with HNN. And I said in we often just control only the connected derived subgroup, the same statement for the connected derived subgroups. And so if you have an L lambda and you send it to the quotient, so this is this here, and this pi is this quotient functor. Then it's of the form m lambda L core external tensor product. And here on the right hand side, you have L lambda and n seen in the quotient. So in other words, when you want to determine the simplification, you can completely pass to this case where m is equal to n. The question is now, I mean, how do you prove this essentially? And since we basically know what h and n is, this tells you what h and n is. But what you see here is somehow rather pretty. You really have that this weight separates in two weights. This GLM minus n weight and the other weight. And so, for instance, if you take tensor products now, let's say you want to calculate L lambda tensor L mu, what you see is basically this tensor product up to superdimension 0 has a Littlewood-Richardson rule in it. And you also have the tensor product rule from whatever the rule is in H and N. For instance, if you take m equal to n, when you don't have the GL term, you have very few, you have a tensor product decomposition, which is only very few summands. But as soon as you have a m different from n, somehow the Littlewood-Richardson rule kicks in and you see many, many, many indecomposable summands up to superdimension 0. Okay, I think I wanted to actually sketch the proof, but this won't be possible. Let me just make the remark here. So I have talked about this h and n many times previously, so I don't want to repeat myself. But essentially, if you take h and n, and at least you take its connected component and you take its derived subgroup, this is essentially a product over groups which are called G lambda. Lambda runs over the maximal atypical weights. Where I basically have some equivalence relation. And then G lambda is either an SL, and so the SL is always the SL in the superdimension of L lambda, or it's an SO or an SP, or sometimes it's something which I write like this: SL superdim L lambda half. This can also happen. And this L lambda always corresponds to the standard representation. So essentially, this gives you the tensor product decomposition up to superdimension 0, because of course for SL, SO, SP, we know what happens. When you go to the m different from n case, okay, you have the additional Littlewood-Richardson rule, but is also well known. And of course, this does not just give you tensor product decomposition between two irreducibles up to superdimension 0. You could take these irreducibles now, you tensor them together, and you look at the indecomposable summands. So the indecomposable summands, they correspond uniquely to certain representations of these groups here, of the G lambda or H and N or whatever. And so of course you can take them again and tensor them together. And then again, the known decomposition laws for the classical groups give you the answer, and so on and so on and so on. So you really get tensor product decompositions, even for very, very complicated indecomposable modules. So that's the picture for GLMN. Let me briefly indicate what is known for OSP. And so this is recent joint work with Maria Gorelik. So the essential message is whatever you can do for GLMN, at least all the beginning steps you can do for OSP. So you can, of course, you can define the semi-simplification. Of course, you can define this subcategory TMN plus. And then I want to have this induced functor. Oops, this is m minus 1. So here, what I mean is, so I'm in the case OSP m2n, and then I write this, maybe I should write it 2n here. Then I have a 2 here. Okay, it's better like this. So I want to have this, and I still have it. That's it's sort of the main ingredient that you need. Without this property, I think you have no way of using this ds functor to understand these groups inductively. And so why is this true? This is based on the following theorem. So if I take ds, and now of course this ds functor depends on an x, but I'll drop it because the way I state it is more or less independent of x. So if you apply this to an irreducible representation, then this is again semi-simple. There's a certain multiplicity here. There are possible so-called parity shifts. And irreducible representations L lambda I. So these L lambda I are completely explicitly given, exactly like for GLMN. And so this basically, the theorem, okay, and furthermore, if the superdimension of this L lambda is positive, then the superdimensions of the L lambda I's is positive. So you have the same positivity property. And this tells you that this ds functor induces, first of all, a functor between Tm2n plus and Tm minus 2 to n minus 2 plus. And then in order to get this induced functor between these quotient categories, you somehow have to check that if you have an object of superdimension 0 and you apply this ds to it, then you get something of superdimension 0. That's highly not obvious, but it's still true. And it would be in fact false if you don't work with these plus categories. If you would work in the full categories, whether for OSP or GLMNs, superdimension 0 does not, an indecomposable superdimension 0 object does not go to a direct sum of indecomposable objects of superdimension 0. And so this desired property still holds. And then basically these Tannakian arguments that I had for GLMN, they kick in, and you can again define this groups H, M to N, and then based on this property here, you get again that if you are on the level m minus 2 to n minus 2, this group embeds into the group for m to n, and you can hope to inductively determine the groups. But that's something that is not done, and it probably would be a lot harder than for GLMN, in fact. And there are a couple of reasons why the picture will be harder. So the hope is, can do the same inductive determination of H m to n as for GLMN. But if you look at the GLMN proof, which I didn't, well, I basically just told you if you have m different from n, how you can reduce to the m equal to n case, because I had talked a lot about this GL and n case previously. But if you look at the proof, basically what you have to do is you have to take the case GL22 or GLM2, and you have to calculate tensor products there. You really have to, by a mix of sophisticated machinery and brute force, determine the decomposition. And then you can say, okay, inductively I know the groups, and then I can use induction. I can say, okay, I'm bet my smaller subgroup, and this gives me a lower estimate for the rank of the big group, and that gives you very strong information about these groups. So there's a lot to be done for OSP. For instance, one would have to do these brute force calculations for low rank, like for OSP 3.2, OSP 4.2, and so on and so on. Then understand the semi-simplification from there. But that's quite hard, actually. And then there are certain things in the OSP case which are not as favorable as in the GLMN case. So I said in the GLMN case that this group HMN is always pro-reductive. There's no super anymore. And that's wrong in this OSP case, because in the OSP case you have these groups OSP 1 to n, and they are semi-simple, they are round. So they destroy somehow your nice combinatorics a bit. Also, if you would just take, if you just would go down by 1 for GLMN, then these multiplicities here would always be 1. But in the OSP case, there would be 2. And so you have somehow branching, which is not multiplicity free, which somehow is a problem in the proof. So, but that's the OSP case. Let me just make one remark here and then finish it. You can ask this determination, basically, starting from below and then going up by means of this DS functor. Is it a general strategy to always attack these problems? And the question is, I don't know. And the thing is, I don't know. So it works for GLMN. It probably works for OSP M to N. But for instance, there is a case PN, so-called peripractically superalgebra, and there DS of L lambda is in general not semi-simple. So this has been studied by Entova, Eisenbart, and Saganova. Doesn't mean that this approach with the DS functor fails, because DS of L lambda doesn't have to be semi-simple for this. It would be perfectly fine if the DS functor preserves these plus categories. So it would be fine if DS of L lambda is an indecomposable summand in an iterated tensor product. That's and then I still think this inductive determination would work. Let me say one last sentence in order to finish. The ultimate dream, maybe, and let me go back to the very beginning, would actually be to do something else for all the groups. So initially I showed you this picture here of these layers. I think of this representation category as layered. And normally one would say, okay, I start with atypicality 0 and atypicality 1, I understand it. And then I go up somehow, maybe by translation functors or so, but it doesn't seem to work. I think what one should maybe say is one controls this atypicality n part. That's basically what we do for GLMN. And then one goes down by sort of not quotienting by the negligible morphisms, but by smaller ideals. And then sort of goes this way. So the hope is to iterate this construction, and so successively, layer by layer, understand these decompositions. But yeah, I think you need a good idea for this, and it's somehow not so easy to find them. Thank you.
Excellent. Thank you so much. Let's please thank our speaker. Does anyone have any questions for Thorsten?
Yes, one question. So you mentioned the case of the periplectic Louis superalgebra. What about the queer, so Qn?
Okay, so there's a result by a guy called Cheng that if you take an irreducible module for Qn, then its superdimension is 0. always, unless you have the trivial module. And so somehow this seems to be uninteresting in the QN case.
Okay.
So in fact, something stronger is true for QN. The super character is trivial. So in the super world, you have the character and you have the super character. The character, you take the dimension of the weight spaces, and the super character, you take the super dimension of the weight spaces. For GLMN, this doesn't really make a difference because in fact, if you have a weight space, it's either purely odd or purely even. So up to a sign, the character and the super character are the same. But for this QN case, you have, if you take a weight space, it cancels out completely. So you have a complicated character, but the super character just vanishes and then the super dimension vanishes.
Yeah, thanks.
Anybody else? Any other questions? Very well. In that case, let me stop the recording and let's thank our speaker one more time.